Today we want to extend our concept to triple integrals, and I was drawing this picture for you at the beginning. Just call that page 0. I may not put it up online. Let's see. Just to remind you what we've been doing in the past, in Calculus 1, you look at this picture. If you want the area under curve, you say, well, this is an important problem. What's a good way to calculate it? I can take this limit of a sum to calculate that exactly with the concept that if I use circumscribed rectangles or inscribed rectangles above or below the curve, and this limit of the sum is the same, then we'll call that the area below the curve. And so if I break this interval a to b into n subintervals, x0 to x1 to x2 up to xn, and I call the width of each delta x1 is x1 minus x0, delta x2 is x2 minus x1, and so forth, then I can say the area of the kth rectangle is f of xk star times delta xk, all right, height times base, and then I sum over all the rectangles. That's an estimate of the area under the curve. The limit, if it's the same, regardless of the partition and the choice of xk stars in each subinterval, like here's x1 star, a point in the first interval where I take the height of the rectangle. This is the same. We'll call that, we'll say it's integrable. And for a non-negative function, we'll also call that the area under the curve. That was calculus 1. For a function of one variable, it's getting the area under the curve by adding up rectangles. For a function of two variables, we said we extend that. Suppose we take a region AB by CD in the plane, and if it's not a rectangular region, then we enclose it inside of one of these and do that extended definition we talked about last time. But for a rectangle, we take this estimate by taking height at an intermediate point in each rectangle on the xy plane. There we go. So in each rectangle, here's maybe the first point. I'll take x1 star, y1 star, and I'll take the height of the surface at that point, and I'll make a rectangular box of that height. And then I'll just do that with each of these things. I'll take the height here and get another rectangular box, and another rectangular box up to the surface height here, it should look like. And we add up all the rectangular box volumes and say that's an estimate for the area under the surface. Adding up all those rectangular box volumes. That's this sum. Sum height times length times width, or height times length times width is the jkth box, and then we let n go to infinity, where n is the number of box sub-rectangles down here, and hence the number of boxes. Gives you an estimated volume, and if the limit is the same, we say that this function f is integrable over the rectangle, and call this the definite integral. And if f is non-negative, we say also that this is the volume under the surface. That's what we did last time. Any comments on that or questions you wanted to add? Is the concept clear? Because now it's time to extend it one more level. Suppose we have a function of 3 variables now, right? We did 1 and 2 variables. Why can't we do a triple integral, right? The triple integral over a solid W, we'll do this in analogy to last time. So this time the domain is a solid, right? In 1 dimension, the domain was an interval on the x-axis. In 2 dimensions, it was a plane region, rectangle being the simplest case. In 3 dimensions, the domain of a function of 3 variables is a solid 3 space. Maybe we'll call it W. Books use different letters. That's not sacred to use W. And we're going to enclose it in some box B so we can do it over a rectangular region in 3 space, a rectangular box. And we'll subdivide this box with J subintervals in the Y direction, capital I subintervals in the X direction, and capital K subintervals in the Z direction, and partition this into I times J times K subboxes. And here's the IJK subbox, little ijk, each summing to the big ij and k number of intervals. What we'll do for this one is we'll say the triple integral is now the function of 3 variables at an intermediate point in the ijk box. So somewhere in here you put a point, xi star, yj star, zk star, that you're going to evaluate the function at, and immediately you have a problem because now you have to draw the function into a 4th dimension. we're computing for the triple integral, we're thinking of a four-dimensional volume, but it's hard to draw, so I won't even try. Instead, I'll just draw the domain here. So this is the domain, just like the rectangle is the domain in 2 dimensions. But just like when you took another dimension, you were estimating the volume below the surface. Now we're thinking of the volume in 4 dimensions of a function that's sitting over the solid, in this 3-dimensional solid. And you take any intermediate point, xi star and yj star, zk star, and evaluate the function there. Multiply it times length times width times height of the box gives you the 4-dimensional volume of the sub box in 4-dimensional space, and then you sum it over all these indices, and adding up all the 4-dimensional boxes gives you a 4-dimensional estimate of the volume, and taking the limit then, if this limit exists regardless of the partition and as long as the width of the widest interval in each direction goes to 0, and you can pick these points in the ijk box arbitrarily, we say it's integrable. So if this exists, regardless of partitions and points picked, we say f is integrable over the solid W. And what we do to do that is there's a little subtlety here, right? We have to define this function f hat that's equal to f on the solid where it's defined, and then outside there, f hat will be equal to 0. And we'll take the limit of the sum, I should have put this in here, of f hat, so that it's defined at all these points outside the solid too. And so we're adding up nothing when we're outside the solid, adding up little 4-dimensional estimating volumes inside the solid. And we'll call that the triple integral. This means it's defined, that says DEF there, to be the limit of the triple sum, f hat, the extended definition where it's 0 outside the original domain, of xi star, yj star, zk star, times delta xi, delta yj, delta zk. And n, little n, is the total number of sub-boxes, capital I times capital J times capital K, right? And so there's the disclaimer. It has to have the widest subinterval go to 0 in each direction. Questions on that one? That's the definition. We'll call that equation 1. You say, how can that be so useful? We don't need 4-dimensional volumes. I'm a physicist or something, an engineer. Maybe physicists might be interested in it, not engineers probably. It actually has lots of nice applications besides volumes that we'll see shortly. But I'll just mention the thing I just did. When the sum exists, we'll call the function integrable. And then, how are we going to evaluate it? Because remember, even in Calculus 1, trying to evaluate this thing by its definition was terrible. How do we evaluate the definite integral? Since this is its definition, it comes out to be a number since it goes between 2 number endpoints. We use the fundamental theorem of calculus. We used antiderivatives, right? Take an antiderivative of b minus antiderivative of a. We needed that theorem to evaluate it because this was too hard, right? Similarly, here, this triple integral is going to be even harder, right? Because it's 3 sums. How are we going to evaluate it? Here's the big theorem. There's just one theorem for this lecture here for how to evaluate this thing. And it applies to this very important case. Suppose that W, the solid, is what's called a simple solid. Its top is a continuous surface. Z equals some function Z2 of xy. And its bottom is some surface Z equals Z1 of xy. So it's a surface on top and a surface on bottom with these 2 equations. And they're both continuous functions of 2 variables, right? And suppose it's bounded on the sides, that is, that's the top and bottom, but on the sides it's got bound such that its shadow in the xy plane, called the projection, is a vertically simple or horizontally simple region, right? The kinds we've been looking at before for the integrals of 2 functions of 2 variables, where it's got vertical lines on the side, x equals a and x equals b, and then it's bound on top and bottom between 2 curves, y is f1 and y equals f2, both continuous. Or it can be bounded by 2 horizontal lines, c to d, with x equals g1 of y and x equals g2 of y continuous on the sides. And we said there's a little bit of leeway. You can use piecewise continuous functions. You have to decide what you mean by, if this has a discontinuity in it, what does it mean to take the area when there's a hole in the side, right? It means you're thinking of rectangles going out to the edge of the hole. Anyway, so some other things, but for this theorem, all you're saying is that everything has to be continuous. The top surface is a continuous function, the bottom surface is continuous. The projection in the xy plane is one of these two types of regions with continuous sides. Then, the definition, the definite integral exists. That is, f is integrable on W. And furthermore, you can evaluate it by this nice theorem. This is the big theorem for today. The triple integral, defined as the limit of the sum of the sum of the sum, is the double integral over the region of projection R. So that when you take a shadow of a solid down in the xy plane, it's the double integral over that shadow from the bottom surface, z1 of xy, to the top surface, z2 of xy, the integrand f of x, y, z, dz, dA, meaning that this inside integral here is a partial integral with respect to z, treating x and y both as constants. And so what have you done with this? You've reduced your triple integral problem to a double integral problem that we did last time. And as long as it's over one of these kind of things, our theorems from the last time then tell us how to integrate the double integral on the outside. So that's a big theorem. Reduce it to a double integral and use your methods from last time. Okay. Here's the picture. This really is what you need more than all those words. I can't tell you how many times I read a theorem and it just befuddles me until I see the picture, and then it's obvious, right? So here's the picture. We'll say that here's a solid, maybe it looks something like an ellipsoid. It's got, and so I put its equator here because we're interested in the top surface up here, z equals z2 of xy. It has to have a bottom surface, z equals z1 of xy, both continuous. So they shouldn't have breaks in them. They should look like a nice continuous object. And then if you shine a light down on them, they have a projection down the xy plane of the edges. That is a type 1 or type 2 region. That's what we're talking about for the theorem. Here I drew it as a type 1. A vertically simple region, but different books call them type 1 and type 2, and I keep saying those things interchangeably. So vertically simple region between x equals a and x equals b for the minimum maximum x bounds of the projection, and then a bottom curve in the xy plane, y equals f1 of x, and a top curve in the xy plane, y equals f2 of x, both continuous. So everything's continuous. Then we can apply this theorem, formula 2, that we just wrote. We write the triple integral as a double integral of a partial integral with two variables held constant. All right, any questions on the concept? Yeah.
I don't, like whenever we were doing the derivatives, like we would do derivatives of like two variables and equals one constant, and then like we did that. And then when we went to 3, didn't we just hold 2 of them constant and do it with, like do the derivative with respect to the third variable? Like I don't see why this, like this seems different, and they don't seem like they're like.
It's the same actually. If you do a partial integration, it's analogous to it's just going backwards on the partial derivative. The question for the people online is when we did a partial derivative for a function of 3 variables, we held 2 variables constant and took the derivative with respect to the last one. Shouldn't we be doing something the same for the triple integral? That is what I'm trying to say here. I'm sorry if I didn't come across. We hold treat 2 variables as constants and integrate with respect to the third variable. That's the inside integral here in the theorem.
So it doesn't have to be like z, like you could do other ones as well, or like.
Yeah, so the second question is, does it have to be z for the top and bottom like that? And that's coming up actually here. There's nothing sacred about doing a top and bottom surface. You can also do a left and right surface and project it into the XZ plane, or a forward and back surface and project it into the YZ plane, and you can do any one of those 3. And sometimes one is easier than the other, exactly. We'll do all the formulas this way, and then the idea is the other ways work just as well, of course. Any other questions? Keep me honest here. So, all right, here's a simple one. We have to keep these examples almost trivial. It's once you do anything non-trivial, trying to do an integral of an integral of an integral, you inevitably come across something that's too hard to integrate by antiderivatives, and you can't finish your problem, right? You can't evaluate it exactly. You just have to run to the computer to estimate this triple Riemann sum, as they call it. That's without the limit. You get an estimate of the integral. Let's try and do this one. The triple integral over, instead of W, I'll call it B because it's a box. Here's the box, and we'll use this notation again. The x interval 0 to 1, the y interval -1 to 1, and the z interval 0 to 2. So the Cartesian product means all ordered triples where x comes from this set, y from this set, and z from this set. It's a box, right? X going from 0 out to 1, y going from -1 to 1, and z going from 0 up to 2 on the z-axis. And if I want to take the triple integral over that, I first look, what's its projection in the xy plane? Well, it's this rectangle. It's just the bottom of the box, right? And then I can apply the theorem and say by equation 2, this triple integral of e to the 2x plus y plus z, which I can think of geometrically as finding a volume of a 4-dimensional solid that's in 3 dimensions this box, and then extends into the 4th dimension you can't draw here to the point 2x plus y plus z to get a 4-dimensional volume. You evaluate that by the theorem by taking the double integral over the region of projection, that rectangle, of the integral from 0 to 2. That's what z runs between. The bottom surface is z equals 0, and the top surface is z equals 2, so you go from 0 to 2. Integrand dz dA. So the inside integral goes first, treating x and y both as constants, integrating with respect to z, a partial integration. Well, here's a trick that you'll see sometimes in the book and other places. People use it all the time. That might make some of this a little easier. Paper here. You rewrite e to the 2x plus y plus z as e to the z times e to the 2x plus y, because you recognize now it's a function of a function of z times a function of x and y only. This function is treated as a constant with this integral, right? It's a partial integral treating x and y as constant, so e to the 2x plus y is just a constant within this integration. I can pull it out. I can pull it out of this inside integral and rewrite this as the double integral of pull e to the 2x plus y out, and then just integrate from 0 to 2 e to the z dz. That makes it a little easier to handle, right? And then e to the z integrated from 0 to 2 is easy. That's calculus 1. That's just integral of e to the z is e to the z. Plug in 2 and 0 and take the difference. You get e to the 2 minus e to the 0 is 1. This integral is just e squared minus 1 now. It's easy, right? Now that's a constant. I can actually pull it out of this integral here. In fact, I can pull it out before I evaluate it since I recognize it's going to be a constant. So I pull it out front. Now I just have to integrate e to the 2x plus y over the region of projection R, which is that rectangle in the xy plane. Here it is. Right? So I've reduced my triple integral to a problem like we had last time, a double integral over a plane region. But we recall that the rectangle in the xy plane, that was the shadow of the big box, that y went from -1 to 1 and x from 0 to 1. So we can treat that as either a vertically simple or a horizontally simple region, right? Let's treat it as vertically simple since that's what we're more used to thinking of from calculus 1, a top curve and a bottom curve. By Fubini's theorem, since it's actually a rectangle, or it's by this generalization, we can call it a vertically simple region, either way. We can say this goes integral from x going from a to b, its minimum to its maximum, 0 to 1. Y going from the bottom curve, y equals -1 to the top curve, y equals +1. But since we have a double integral in this case. And so now we just need to integrate from 0 to 1, ab, and -1 to 1, c to d, e to the 2x plus y dy dx. Well, just like in the last example, we rewrite this as e to the 2x times e to the y, and within the integral with respect to y, e to the 2x is a constant, so I'll pull it out here and rewrite this with this thing still multiplying outside, e squared minus 1, as the integral from 0 to 1, e to the x, because I pull e to the 2x, because I pull the e to the 2x out, it's a constant within the partial integral. times e to the integral e to the minus 1, the 1, e to the y dy, all integrated with respect to x. So I pull the thing that's treated as a constant out, e to the 2x. And now I recognize this going between constant endpoints. You can only do it if it goes between constant endpoints. If these depend on x, then this is a function of x. You can't pull it out of this integral. But because this is evaluated at constants, this is a constant. You can pull it out of this integral and write this as integral 0 to 1 e to the 2x dx, pulling the dx through this constant out, integral minus 1 to 1 e to the y dy. In fact, I could have done that at first, broken this into a product, integral e to the z from 0 to 2 times integral e to the x from 0 to 1 times integral from minus 1 to 1 e to the y dy. That only works over, when you look at this and say, oh, that's a constant, you can pull it out. So be careful on that. But it has to be a product of x times product of y times a product of z for the integrand, so you can pull those constants out like that. Well, you'll see that trick, so I wanted you to see it here in class first. These are easy to integrate, right? They're calculus 1 integrals. E to the 2x has antiderivative 1/2 e to the 2x. I can plug in the endpoints and take the difference. That's how we evaluate those integrals in one dimension. Integral e to the y is e to the y. We just plug in the endpoints and take the difference. And what we get from evaluating these is e squared minus 1 times 1/2 e squared minus 1 times e to the 1 minus e to the minus 1 for this one. So there's the volume of the four-dimensional box, or better, more generally, the triple integral evaluated by this theorem we just got. But that's the whole section. It's a one theorem section. If you look at it, you need the evaluated triple integral. You rewrite it as a double integral of a partial integral with two variables held constant. All right. Well, with that, until we can carry it a little further then. And I wanted to point out something. This isn't just for mathematicians, actually, because it has this important application. And this is the other part of the section. It's not a new formula. It's just saying, here's what you can use it for. A triple integral of a function that's a density actually gives you the amount of whatever quantity is enclosed. If f of x, y, z is a mass density, like kilograms per cubic meter, right? And you take the triple integral, we say that is the enclosed mass. So you integrate the mass density over with a triple integral, you get the mass enclosed, right? So many kilograms. If you integrate a weight density, then you get the weight of the object enclosed, right? That's so many pounds per cubic foot or something, and then you get the pounds of the object. If you integrate a charge density, you get the total charge enclosed, right? Those interested in electromagnetism will appreciate that. So you integrate all the charges. Essentially, you're just summing all the charges inside and taking the limit, because you have an odd-shaped region. And so that's what the triple integral does in practice, is it evaluates a quantity enclosed through integrating its density. So suppose we have this kind of a problem. Find the mass of the tetrahedron, right? A object with 4 triangular sides. If its density function, f of x, y, z in general, can be, it can vary in x, y, and z, is equal to x. So it's some simple thing where we had a molten metal and we let it settle, and it only got denser in one dimension because of gravity, right? All the heavy stuff came down the bottom and the light stuff's at the top. And suppose, this is a little unrealistic, but suppose its density as a function of x, y, z is just x. It's a very simple function. Again, we have to take almost trivial examples or we can't do the integrals. So if its density is x, and this is what it looks like, it goes through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. What in the world is its mass? Well, the mass, remember, is the triple integral of the density. So all I have to do to evaluate that is take the triple integral of x dv over the solid w that is this tetrahedron. So now how do we set it up for that thing? That's the hard part of the section, is figuring out how to set up. What is the projection? what is the top surface and bottom surface, all that kind of stuff. It's only one theorem, but it has lots of these quandaries you can get into. What am I doing? Well, if you look at this, there's at least two ways to find what this is. Here's what we're saying, is it's bounded on top by this plane that goes through these three basic points, right, the unit points here. And it's bounded on the back and side and bottom by the coordinate planes, is the idea from the picture. So there it is. And in order to do this, we need an equation for the top surface, this plane, and for the bottom surface. Well, the bottom surface is easy. It's just the xy plane, z equals 0. So the bottom of this solid is z equals 0. I'm going to just put that on here. So this region here, R of projection, is the plane z equals 0. What about the top surface? Well, the top surface, there's a couple ways to do it. One way is to say, well, if it goes through these 3 points, it has equation x plus by plus cz equals d. Most generally, we can put ax plus by plus cz equals d. But if a isn't 0, and it's not in this case, since it's not a vertical plane, we can divide through by a and say this is the general form of an equation for a plane where it's not it's not an extrusion in the x direction. So now we can just plug in these 3 points, 1, 0, 0, 0, 1, 0, and 0, 0, 1, and get 3 equations for the 3 unknowns, b, c, and d. And you can always solve for b, c, and d. So that's one way to do it, is write down the general plane equation divided through by a, since it's not an extrusion from the xy plane. And then plug in the 3 points. These are actually easy equations since I took trivial points. If I plug in 1, 0, 0, then I get 1 plus nothing equals d. Oh, d must be equal to 1. So now I know d is 1 over here. Now I plug in 0, 1, 0. That makes these 2 terms fall out, and I get by equals 1. Oh, b must be 1, right? And then I plug in 0, 0, 1, and I get cz equals 1, because I found out d equals 1 in the first step. And c must be 1. So it's the plane x plus y plus z equals 1. You can plug the 3 points in and get 3 linear equations and 3 unknowns and solve them. See if I wake you up here late in the period. Always the time. It's like 7th inning stretch always at this time. Right? You ever been to a baseball game? Everybody falls asleep about that time if they don't eat something and stand up. Baseball was the most popular sport when I was a kid, and it's kind of lost its excitement because we're more interested in action, I think, these days, football and basketball. Great sport, actually. What's another way to find the equation for the plane besides plugging in the 3 points and getting 3 equations and 3 unknowns? But remember, how do we usually find equations for planes early in the semester? We had a point normal form, right? If you had a point and a normal vector, you can immediately write the equation for the plane. This one, the normal is obvious. By symmetry, the normal to it is the vector 1, 1, 1, right? So I know immediately 1x plus 1y plus 1z equals d is the equation for the plane, right? Because a, b, and c are the components of the normal vector. So 1x, 1y, 1z equals d. And now all I need is to plug in a point, right? That's the normal vector. A point, I take any one of these, 1, 0, 0. So start with the equation 1x plus 1y plus 1z equals d. Put in 1, 0, 0, I find d equals 1. I've got it faster even, doing the 3 equations and 3 unknowns. So if you can figure the normal vector easily like that, you can do this really quickly. So use either way. I'm going to give you a simple one on the test, but maybe even the same one, who knows. I can't make it much harder. You'll be all day you spend the whole test doing this one problem. But there's the plane. Now this is the top surface, x plus y plus z equals 1. How do I convert that into this integral? I'm trying to evaluate this triple integral, right? Well, I need to go from the bottom surface to the top surface on the inside integral, and then the theorem, equation 2, says I take the double integral over the region of projection R from the bottom surface to the top surface. And so if the bottom surface is the coordinate plane, so it's just z equals 0, I put the bottom in point 0, but the top and the bottom in general can be functions of x and y, and indeed this one is, right? I just solve this plane equation for z, right? Z equals 1 minus x minus y, and that's my top endpoint. The surface is z equals this. That's z2 of xy in the theorem. And this is Z1, is just the constant function 0. All right, so this is a little tougher than the last thing because we're not just integrating over a rectangular box, but up to a surface that's a function of x and y. Top surface, bottom surface on the inside integral. Then we've got a double integral of that to evaluate. How can we do that? We can actually do that all in one fell swoop. But I'm going to do it in pieces here. But I'll mention the one fell swoop later. To evaluate this inside integral, remember integral with respect to z, you treat both x and y as constant. Now I can't pull this out of the integral here because this is when I evaluate at the top end point, it depends on x and y both, right? If this integral is a function of x and y, I can't pull it out of either of the other integrals. It's not going to be a constant, so I can't pull this one out. I'm just going to have to do it. I'll say the integral of x, treating x and y as constants, is just x times z, right? Then I have to plug in the top function, the bottom function, and take the difference. All right. So xz, plug in 1 minus x minus y for z, gives us x times 1 minus x minus y. Plug in the bottom end point 0 gives us nothing. So now I have to do this double integral over the region of projection R in the xy plane. And again, there's nothing sacred about doing it that way. You could also project it into one of the other planes and integrate with respect to y or x on the inside. Well, let's multiply that out. I've got x minus x squared minus xy integrated over this. This was the region of projection, right? This triangle was the base of the solid. I should put this back up here. Here's what we're integrating over, mind you. This tetrahedron. The bottom here, face, is the projection. It's the shadow. And it went to 1 on the x-axis and 1 on the y-axis, so I know immediately this triangle goes between 1, 0 and 0, 1 in the xy plane. This is the triangle right here, right? The bottom face of the tetrahedron. Now I'll call that R. And now to evaluate a double integral, I need to go treat it as vertically simple or horizontally simple. We'll treat it as vertically simple because it's easier to think that way usually. X goes from a min to a max, 0 to 1. Y goes from a bottom curve to a top curve. Y equals 0 to y equals 1 minus x. You have to write y as a function of x for the top and bottom curve, go from bottom to top to do a double integral. And so there's the theorem from last time. Min x to max x, always constants. Min y to max y, functions of x's. Now I said I'd tell you how to do this all in one fell swoop. Let me just write this down here. No, you could also do this from the beginning like this. You could say it was the double integral of the integral of z going from 0 to 1 minus x minus y of the integrand x dz dA, and then if I evaluate the theorem from last time as dy dx, a vertically simple region, x going from its min to its max, 0 to 1, y going from the bottom curve, 0 to its top curve, 1 minus x, then there's what we can do all in one fell swoop, right? This inside one is applying a theorem we did today, together with the theorem from last time to evaluate over a vertically simple plane region. We go from bottom curve to top curve, min x to max x. So you can write that all out. The triple integral can be written as integral from min x to the max x, bottom curve in the xy plane, f1 of x, to the top curve, y equals f2 of x, continuous functions, so the integral exists. Again, this works for some other things like piecewise continuous functions. And then the bottom surface, the plane z equals 0, to the top surface, 1 minus x minus y. Hope you can read this. My pen's going top surface. Z equals 1 minus x minus y, the tilted plane. That's what you do, min x to max x, bottom curve to top curve, bottom surface to top surface, when you do a vertically simple region. If you do a horizontally simple plane region to projection, then you'd reverse this dx dy. Y would go from min to max, and x would go from left curve to right curve, using last time. Well, you do that all at once, And sometimes that's easier once you get used to it. The idea is to try it with theorem first, just change the inside integral and do a double integral of that and do it in steps like I did in the notes here. But in the long run, you can do it the fast way all at once like that if you like. So here's what we have, this double integral. And we can't pull this out because it's a function of both x and y. It's not a function of x times y. If I had a function of x alone, I could pull out of the y integral, but I can't here, right? So be careful on that. Don't pull an x out of a y out of the y integral. I'll just have to integrate this term by term. So the integral of x is xy, right? Because we're treating x as a constant in this partial integral, right? In the inside partial integral, we treat, with respect to z, we treat x and y both as constants. And in the second integral, with respect to y, we treat x as a constant and z is gone. So x squared y from this one, minus xy, x is a constant, but y is the variable, so it's minus xy squared over 2. Right? And we have to plug in the top and the bottom and take the difference. 1 minus x and 0 is plugged in for y. And that means we replace y here with 1 minus x. So the way you do this carefully is everywhere you see y here, you replace it with parentheses and put in 1 minus x. So x times parentheses, put in 1 minus x squared times parentheses, put in 1 minus x times parentheses squared over 2, put in 1 minus x. Now you've got it, right? That's the careful way to do it. And now I'll warn you, you start to see that almost any time you do a triple integral, it is really complicated. Look, when I multiply this out, this is just simple low degree polynomials, and already look at all this. So I multiply it out, x minus x squared, that's that one, minus x squared plus x cubed. Let's see, x minus x squared plus x cubed. I'm checking to make sure I don't make a mistake as I go on. And then minus, I have to FOIL out this 1 minus x squared. It's 1 minus 2x plus x squared, all times x, all times minus a half, and that's where you get in trouble with. So let's see, this is minus x over 2, yeah, plus x squared, minus x cubed over 2, looks like when I multiply all this out. And so now you can collect like terms here is a good idea, make your life easier, right? So I'll collect the x cubed terms. I've got x cubed minus a half x cubed is plus a half x cubed. Minus x, here's minus x squared and plus x squared that cancel leaves me minus x squared. And then x minus x over 2 is x over 2. That's not so bad. Now I can integrate with calculus 1. I get a sixth, let's see, an eighth x to the fourth here. A third x cubed is the integral minus of x squared. Integral of x over 2 is x squared over 4. I have to plug in 0 and 1 and take the difference. Now it's just down to fractions, right? I plug in 1, I get an eighth, minus a third, plus a fourth. Plug in 0, I get nothing. So I get 1/24 out of this. Apparently this thing's mass is 1/24 kilogram if the density function was in kilogram per cubic meter, and I integrated over meters here. So you have to be careful of the units in minutes. But that's it. That's the big application, is to computing masses. And actually, as we go along here, we're going to have a section coming up shortly where these triple integrals can do other related things like moment of mass. From the moment of mass, you can calculate the center of mass. If you have a flat plate, you want to know its balancing point, you can do it with this triple integral also. Where you have a solid, you want to know where's its center of mass. There's this kind of thing that appears in a lot of physics books, right? You take some oblong object, right? There's a peanut or something, right? And I throw the peanut through the air. How does this motion go? Well, if I treat it as a point mass, I can take this point here and it kind of goes like this, right? What a mess. But if I take the center of mass, ignoring air friction here, center of mass in constant gravity, it goes a nice parabola, and it rotates, the whole thing rotates as it goes, but the center of mass just goes a nice easy parabola, and that one point is very important because that's the one point that has an easy trajectory, but you can calculate with these triple integrals we're going to find. So there's some applications coming up. It's not just four-dimensional volumes for abstract mathematicians. All right. Any questions before we go then? I hope it was insightful. Try those, and what you see is you get these terrible integrals. What we want to do next time is say, well, what can we do to make our integrals easier? Maybe I get one I can't even do the integral. What you can often do is change to a different coordinate system that makes the integration easier. Like if it's a sphere you're integrating over, you can use what's called spherical coordinates, right? And Then the equations for it's really easy. The resulting integrals tend to be easier too. So that's the next thing, is to try and do these multiple integrals in other coordinate systems. Thank you.